Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. So let's continue discussion on air bearing systems. So we have been talking about air bearings, and by now we understand why it's so important to have the air bearings if you want to have a very precise motion, if you want to develop any kind of ultra precision motion systems, and where we looking for accuracy or repeatability of the order of microns or some micron levels. At least that's the bare minimum. So we'll try to discuss one of the stages, one of the air bearing system we developed. So for instance, this is the system I developed when I was working in Singapore at Simtech, A-Star, and it was basically how to achieve ultra precision, but at the same time how to achieve high speed motions. So if you look at it, so mostly, so these designs, if you check currently, the stage, various motion stages, so either it will be gantry or stacked configurations, and you have guideways, and what you notice that these guideways, the linear guideways, are running on air bearings, and it can be orifice type or it can be porous type. So those are the configuration and those are the elements. So we'll try to understand the requirements and how to achieve those specifications right from the beginning, how to ensure that we can achieve that. So of course we are looking at very precise motions, so ultra precision motions, and in many applications we have to really move very fast and a start and a stop kind of motions we have, and we want to get rid of any kind of jitter or any kind of vibrations. So want to eliminate and want to achieve those motions very fast. So for instance, if we are doing wafer scanning or some inspection we are doing, and or even pick and place or in many kind of SMT devices. So these will be our requirements. So when we look at it closely, what we realize that yes, the load is there, load and stiffness plot for air bearings, and this is the air gap we are talking about. So if there is any change in the loading or any change in the air gap, we lose stiffness, and for high speed application that may not be desired because it affects the whole dynamics. So and sometimes this change can be very large. So stiffness change, if you see there is a small change in the air gap and there is a huge change in the stiffness properties. And why is there, we can easily see with this animation. So this can be your, so this is the granite bar. So usually we use granite for this kind of applications, for any precision application, and this mainly because of the structural integrity and the temperature variations and the moisture and all those aspects. Looking at those different aspects, the variation in the dimensions is very small, it's so rigid, and that's why in many of the precision application these days you see granite blocks. So it's a granite, uh, and polished, and the parallelity and the flatness all measured. But definitely there is a limit, and within the tolerance limit you will find that okay, it's no more flat or no more parallel. So if we simply exaggerate, and what we see in these plots are, so the reference surface and this, yeah, so both surfaces can be like that. So if you are using the reference surfaces, but as we move, what we realize that these dimensions are, again, is even if it's a plus minus 4 micron, or if, so parallelism, how to achieve that parallelism, that's a big question in fabrication, and getting below 4 to 5 microns is really challenging. And if it's not, and whatever is the residual tolerances what we have is going to change these air gaps. And if there is any air gap, but you see that there is a huge difference in the stiffness, which is not desired. So although air bearings are very good, but these are the limitations when we are trying to put them together and try to, if we simply characterize and try to see the model characteristic or try to measure the stiffness values, what we realize that there can be huge difference, and it can be related to or accounted for these kind of variations. So yes, the parallelity is very important, how parallel the two surfaces are. I think that's something we need to understand. So usually in most of the design there are two parallel reference surfaces, so we try to make them flat, make them straight as much as possible, and we also use them for use that as a guide or use as a reference. So there are two parallel surfaces. So how to maintain that parallelity and how to achieve that. And if it's like two separate parts, so in this case what you see in both the examples is on two separate pieces. So during the assembly we have to ensure that they are parallel. Of course, the local deviation, the straightness will also affect. So, and what we see the change in stiffness because of that. In two parallel reference surfaces, what we rely on is the averaging, because yeah, it both from both sides is acting, so it's preloaded, and okay, it will come under equilibrium, so air gap will be same on both the sides, and that is the lateral positioning error, what we can say, that's possible to achieve if we are just using these principles, these two principles. So the idea was, instead of using these two reference surfaces, is it possible to use only one reference surface? So one surface as a reference, and whether it's possible to just use that, and the other we try to manipulate, we try to adjust, and whether it's possible. So conflicting requirements are there. On one side, what we are saying, use only one reference surface, so we can use that surface as good as possible, the straightness, flatness, everything. So then we follow that surface, and how you follow? If we move along the surface, we try to maintain this gap. We try to maintain same air gap throughout. So of course, then we can mimic the reference surface. So, and any error which is local, that can be compensated, because if it's repeatable, then we know where is and what is the error. So we can achieve repeatability. But how to achieve that air gap? So assuming there is some kind of magic here and a block. So we put the air bearing, and then so this is one bearing. This air bearing is another one, opposing air bearing. So co-located. So to get the required preloading. Behind, what we do is we put a readjustable system and try to maintain constant air force, constant force. So if the force is constant, from the air bearing characteristic, we know that the air gap will be also maintained, and if we can maintain that air gap, so we can maintain the stiffness as well. So that was the logic, and that's what we try to do. And so preloading is very important. So what we also learn in design is form closure and force closure. So where we try to achieve these dimensions through geometry, that is form closure. So we fix the dimensions and work towards getting tighter tolerances so that there is no deviation. So that is form closure. So it's by the geometry. Here the principle is, at the other end we are trying to develop a preload mechanism, and this is the constant, so that it always applies the same preload to the air bearings, and so that it closes the gap and then it maintains the same air gap. So form versus force closure. So these are two different approaches. So many times force closure we use. If we are not aware of, we resort to form closure, and then we are completely dependent on the tolerances to achieve a high precision. Wherever we are talking about compliant mechanisms, most likely will be talking about the force closure. So we let it deviate, but we apply the same load. So how we can maintain the same preloading all the time as it moves? So there can be active means. So we can have actuators sitting at the back. So many of the designs, they have this. They have piezo actuators, and it always works in closed loop. You measure the air gap, and accordingly you change the preloading. So of course you can get a very high preloading, and you can achieve very high stiffnesses as well. Of course, the control is one aspect. The other thing is the hardware, the requirement. Yes, it's a complex, and at the same time it can be very costly also, because you are adding additional hardware and the piezo actuators, the sensors in the lateral dimension. That will be required, and it may not be so cost effective. So definitely, if we want to achieve very high precision, and yes, means the cost is not the criteria, we can always go for high end and look for these kind of actuators and can use it. What if we can use the passive means? So I think what one has to be aware of, if it's active means and piezo actuators, not just any actuator, but piezo actuators, what you realize that the stiffness, you don't compromise the stiffness, and that is the good part, because you can achieve very high stiffness. So overall the dynamics of the system is preserved, and you can manipulate that. There can be different approaches. You can always have a co-located actuators, or we can also try to find the nesting force. So we can have the nesting force approach, and depending on how many degrees of freedom you want to control, based on that we can also use those kind of that many actuators. So again, it's a very nice topic, and once it comes to implementation, I think that would be great, and this is where we can put put things together and can test it and can see whether we can really achieve that. So this will be really interesting. And to start with, we can always go with the passive means. So pneumatic actuators, or we have disc springs. Pneumatic actuators, yes, the stiffness is a question mark. We cannot have a very high stiffness. Yeah, of course, we can get high load, but the problem is it can be very bulky. Disc springs, yes, high load it can take. The stiffness is comparable. Yeah, it depends how we put them together. So bell springs, uh, is disc springs, and it has a different characteristic. Depending on how you put them together, we can achieve different stiffnesses. So that we'll see. Of course, it's easily available, so very cost effective, and we can try it very easily. And if you get a chance to open any or overhaul any CMM machines or older machines using air bearings, you may realize that these things might be there. So this was the philosophy, the concept that we fix the loading, preloading, so that the air gap is maintained, and therefore we can maintain the stiffness also. So now you can imagine that is suppressed with this force, and then when it slides, and this is the reference surface. So this is the reference surface we are talking about. So it can be flat and can have a very good straightness, and then it can follow. And so even if the straightness is not there, but if we are able to get this location wise, we know what is the air gap and what is the deviation, we can always compensate. So try to implement that, and just what you see is air pad here, air bearing. So the granite block is on the top. So it's a so this black is the porous air pad through which the air is um, flowing out. Uh, what we also see here is, yeah, so how is we are supporting, that's very important. So we created a spherical joint so that it can self align. You can see the disc springs here. So we designed this adapter module, so which has a way to put the disc springs, and it can be adjusted. So we have the load cell here for the measurement, and here you can see threaded. So if we turn, we can press it. So and then it deforms, the disc spring deforms, and it applies that preloading to the bearing surface. So that was the idea, and this is how it's designed. So all aluminum, so lighter material, and of course we have to also look at the stiffness, because all are preloaded. So it is applying forces in the perpendicular direction all outward. So it will bulge, and if it's open construction, you know, the stiffness will be very low. So I think the stiffness, from a stiffness point of view, we have to also look at the design. So we cannot have a very thin structure, otherwise it will bulge out. At the same time, we cannot have a very bulky system, because then the overall weight, the payload capacity will get reduced, because this itself can be very heavy, even though it's of aluminum. So some of the features you can notice. So I think the bottom and top. So if you see, there are three air pads here, and yeah, coming back to the stiffness parts, you can see a lot of pockets. I say it's mainly to reduce the weight, but at the same time you want to have a very high structural stiffness. So If there is a force, it should not deform. So a lot of pockets, and we try to remove most of the materials. So 3 bearings. So 3 bearings, we know that it we can support on a planar surface. So 3 is enough. So we use 3 on the top, and for preloading we use the 3 of these modules. It's a co-located, so directly opposite to that. And with this turning of these threaded screws, we can change the preloading. So yeah, similar kind of arrangement. Only thing is on the top the bearings are directly mounted, and of course we can have a fixture so that it can self-align. So ball and cone kind of fixtures. At the bottom we have that flexure. We can say it's a compliant mechanism, but basically it's a disc springs. We are using disc springs. So three constraints, very good. What we realize from the sides, we have again 3, and this is something as a fresh engineer, you always doubt, and you have some iota of doubt, and you feel, oh, whether it's going to work or not, and you always go towards putting more numbers, and then you don't realize that actually you are over constraining. So 3 plus 3, so 6 constraints total, but you want to only move in one direction. So what is required is 5C. So one constraint is extra, it's over constraint. So this is something you learn while doing it, and actually it gave me a lot of problem, and slowly you have to learn how to adjust it, how to fix it. So then what I have done is 3C plus 2 I use. This one was very slowly, very precisely you have to, so it was more like a slave. Slowly fine tune so that it doesn't create any problem. But with the air bearings, what you realize, moment you tighten it a little bit, it over constrains, and then you start having vibrations, pneumatic hammers, all those kind of problems. So I think those are some lessons you learn when you really start working on those systems. So 3, it should be 3 plus 2, 2C should be enough. And moment you have this extra one, actually from the top also that DOF is constrained, from the bottom also you are trying, it's a fighting. You are trying to constrain the same rotational degree of freedom, and that's why you have a problem. So that's something we have to learn and understand. Yes, we have to also make provision for the linear motor, so you can see the linear motor here, and we also have the encoders placed so that there is a grid, so gold bar there, and it can be stick to um, the surface of the granite block, and you can measure where you are. So it's a probably I think 10 nanometer resolution, so you can get a very high resolution encoders these days. So linear motor, everything. So yes, means the CAD model these days very powerful. So it was done 20 years back, but I think if you see the packages these days is way advanced now, and we can do. But nonetheless, that even at that time you are able to do a lot of things, and can see yourself that whether things can be put there, and the dimensions you were talking about, can you achieve that? And the rendering, the CAD model, you can see is, it looks so beautiful, but that is not the intention. The intention is to put as many details as possible so that you know that what can go wrong, and if there is any doubt, any iota of doubt in putting anything there, it means something is missing, some clarity is not there. So many times as an engineer, you say, oh, we can do that, we can take care of those things later. But you realize that actually that is something missing, and that is going to give big headache, big problem when you are really going to integrate and do the testing, because that's something not clear to you at that moment. It means how it will be better later. It can't be. So therefore, it's very important that that clarity, that visualization, the 3D visualization we generally talk about. So even in engineering, what we talk about in the first year, we talk about the visualization. Yeah, many people misinterpret it, and many times you simply think about the drawings and just making the cats. But it's more than that, and it's more about the visualization, the getting that clarity in your mind. And for an artisan, for an artist, for an engineer, it's very important to have the concept, have that 3D perception of what you want to build. So if something is missing, always try to break it, try to build it in your mind, and sketch, try to make sketches, try to make the CAD, because if you are able to make the CAD, highly likely you will be also able to get it. Yes, in terms of dimensions, yes, CAD, any dimensions you can work, whether it's nano or macro or meters or kilometers, it's just a number to a CAD package. So you have to be aware of those dimensions. But if you are able to put them together, and if you are able to animate and see yourself that things are working, highly likely things will work in reality as well. So it's very important to put the details, work on the details. And many times in the industry, in the companies where I worked, there is a saying, the devil lies in the details. So once we start putting things together, the nuts and bolts and the screws, and want to put them together, then we realize that where is the problem. And sometimes those problems can be very challenging, and sometimes there is the question mark. So how to solve that? So don't underestimate the CAD modeling part. Spend time and put the details. So we try to put all the details. Even the pedestal you see here is a 3. Yeah? So because this is exact constant design, so even the structure you see, the rigidity, the tetrahedron, we try to preserve. So those are little things, but if you are aware of that, you can easily notice it, and you may be able to appreciate that why it's there. So once it comes to realization and fabrication, yes, we need to have a very good support, and it's not only the design but the execution part, getting those parts, individual parts, to the tolerances mentioned. That's very important. And yes, workmanship and a team working on these kind of things is very important. So good thing was, once it's a design, and if I can just give the part drawings to the manufacturer, they can come up with all these parts in time with the very good tolerances. So it was very easy to work with. So you can see yourself that how things can be done on the shop floor. So it's slow, one by one you put them together. These are air pads and the pneumatic tubes you can see. So slowly you put them together. You also assemble these uh, bearings. Sometimes you have to also have to be a little bit creative and resourceful. Sometimes some parts may not exist, so you may have to use some other parts differently. And some kind of glue, adhesives we also used. So I don't see any difference from the CAD to this, because everything is there now. And the linear motor, you can see we started putting the linear motors, and ultimately one can see that how things are stacked. So you have the frame, and then you have the granite block, then this is the H bridge, right? The granite bridge, and then put the from the three side you assemble things, then put the linear motor encoders one by one. So it's not, of course, not a one-day job, but I think once you start putting them, you understand and you also start appreciating. And once it's done, and once you activate, once you supply the air pressure, you find that it's so nice it, because the flooring is also not a rigid floor, it's specially made flooring, so that the ground vibration should not uh, pass to the system. So once you step in the area, actually it deforms. So even that 1 degree kind of thing, actually it will start sliding towards one side. So you can just poke with the finger and it starts moving. So that's the beauty, because here, although the weight is there supported and on the bar, and then okay, whatever end the weight was, maybe of the order of 10 kg. So 10 kg you put on a surface and try to pulse. It might not be easy but in this case mu is almost negligible, and of course you can simply poke it and it starts moving. So of course the inertia effects will be there if you want to move at a very high speeds, but it's mainly inertia. So I think this is the time I think we should also take it, and if this kind of development we start doing in India, definitely we can support the industries who needs these kind of systems. So that is one requirement. The other requirement is, of course, we need to characterize, we need to see, measure, and we should be able to measure to that level. So these days, I think the micron is already a big number, so it should be some micron level kind of measurement we want to do. We want to do the repeatability, how repeatable it can be. So it's so interferometers are there. These are older one, but these days I think very small versions are now these days available, and that can be easily plugged, and no need to use this very big setup these days. So and this can be easily implemented, and in ASML machines or in even other machines, uh, these are now. So yeah, we didn't talk about metrology frame, but there is also a metrology frame where we all put the sensors and different kind of sensor and optics, so that the any kind of the machine dynamics, it should not affect the measurement. So measurement should have a different metrology frame. But uh, coming to the instrumentation part and the characterization part, this is required if we want to develop any kind of systems, and a lot of optics involved here. So we put it there, and then we can also place it and can do the measurement. So these are like bare minimum, and these are something which will be required, different kind of flats, different kind of labeling tools, interferometers, and if you are going for a dynamic application, even the piezo actuators, the different kind of sensors, a capacitive sensor, inductive sensors, so which works in that range, in the micron range. So we try to do the measurement first for the granite block, and this is how we did. We put on a surface place and try to do the measurement, and so that we know the flatness, the straightness. For this is the spring I was talking about, the Belleville springs or disc springs. So it is a non-linear springs, but very good, and it can be stacked. So we tested it, also try to characterize different kind of springs, and we just put them together in this adapter, and also try to characterize it. So we put the load and the displacement. What you see here is a hysteresis plot, and you may be wondering why it's there. And of course, at that time it was not very clear. But now if I look back and after knowing the effect of friction and how the friction and the stiffness can create can give us this kind of hysteresis and the virtual play, I think now you will be able to uh, understand why it's there, because the disc springs, they are sliding. If there is a micro slip, if there is a deflection, they are stacked on top of each other. And if that is the thing, if there is a deflection, of course it's a friction based and the stiffness is limited, so bound to happen the hysteresis. So it should not be a surprise now. Of course, at that time, if you are not aware, you keep scratching your head why you are getting this kind of hysteresis plot at that time. But now understanding the how it works, because now you are loading and this disc springs. Remember the CAD design is stacked, and then if you are loading, they are deflecting. So there is a relative motion between the springs, and that will lead to hysteresis. So we also did measurement, and the stress net plot we did, and apply different pressures. So wanted to study that as well, and also talk about the loading. So mind loading, preloading, no means there is no preloading from the bottom end with the screw, but of course there was a preloading because of its own weight. So, but there was no extra preloading added, and this was the measurement at different locations. So we stopped at one point and tried to measure along that length and moved, and that's what we are getting. Similarly, we increase the preloading by tightening this screw, and again moderate level we increase. So now as we increase the preloading, what you can see that is now converging, and to a particular location is not changing much. And so what we realized that if we have a high preloading, and that's what we understood, if the loading is high, the preloading is high, the air gap is getting reduced, and that also leads to like a better repeatability, and that we also observed here. So better repeatability at higher preload. So higher preload is very important. So we did another one again at a different location. So preloading we changed, and that's what measurements you see we try to move around. And again the loading we change, preloading. The pressure is usually 4.5 to 5 bar. We try to increase, but then we encountered a pneumatic hammer. So that's why one has to be careful. And of course, there are certain things we don't have an answer now. But I think while working, and maybe we can look at the literature and can also see correlate the data. Also, although the porous air bearing manufacturers, they claim that it's immune to pneumatic hammer, but in reality, in practice, when you start building the system, you encounter the pneumatic hammer even in those cases. So yes, you have to also always take those words from the manufacturer or the catalog with a pinch of salt, and and you know the problems only when you start building things using those modules. So if it's low, if you can see the variations, and when we try to put them together, what we realize that if the preloading is high, the repeatability is of the order of 0.88 micron, And one way to also see it is supported at these 3 points, and it's a gliding. So at the individual level, you have a different measurement, 1 and 2, but if you take any measurement at any point, it will be always an average of the 3. So it cannot be more than the 3 if it lies within that boundary, within that triangle. Of course, if it's over, then it will get accentuated and the error will be larger. But we'll get a very good averaging. So averaging of errors we'll find, and better repeatability at high preload. So preloading is one of the things I think we have to always look into. What we also understand and realize that, so low preload, and what we try to do is again try to measure, and one is when the pressure was not on, so it was sitting on the surface, and then we apply the pressure, and then entire thing gets lifted up. So of course, from the first plot itself, you can see that it's mimicking the surface. But when you just plot for the lift, what you realize that is of the order of 8 to 9 micron at low preload. When we increase the preloading, that has reduced to 2 to 3 micron. So now you can imagine that what is the air gap, what is the dimensions where you are working. Yeah? And it's not like those machines, hovercrafts, right, where the gap is like in centimeters or so. But here, the lift, the gap you are talking about is of the order of 3 micron. So of course, the preloading is very good. It's very good for repeatability, but the air gap now is of the order of 2 to 3 microns. And if that is the gap we are talking about, then what is the flatness requirement of any surface? Can we get? Because things can easily get stuck. So the flatness requirement, the surface quality of the granite block requirement is very high. It has to be within microns, and not just within microns, but maybe of the order of 0.2 or 0.2 micron. Can you achieve that? So that is a challenge. So if we want to do business, want to develop systems made in India, we have to also ensure, we have to also check if we are getting granite blocks from Rajasthan or whoever is the supplier in India, how to get that? What kind of requirement is there? What are the processes? So of course, Moore Lab and in US, in Cranfield, in Europe, they have mastered the art and they have this huge system. So of course, we need to understand the limitations of machine learning and AI. They cannot make these flatter surfaces, but these flatter surfaces are required if you want to do more and more AI. So we have to think about this cycle that AI needs chips, but the chips needs these tools. And these tools, how it's made is many times it's a handmade by the mechanical engineers, by the electrical engineers, the core engineers. Yeah. So I think we should focus on core engineering also. We should also try to develop. Then only we can move forward and we can support. Otherwise, we'll be always dependent on the foreign companies to supply this kind of product to us. So if you really want to, I think we need to understand the requirement, and we have to also put efforts, put resources to build or develop these kind of facilities so that we can, one day we should be able to achieve these kind of systems. Again, now looking at the high speed, so we tested for 2G, 2z is right 2 into 9.8 meter per second square. So this is the acceleration. G means 9.8. So, but these days we are talking about 10, 20, 30 g acceleration, want to move very fast. So even with the half g, if you try to actuate and want to give that acceleration, but you realize that there will be a lot of vibration, the impact you can see immediately. Slider moving from one place to another, stopping, it may not be getting a very high speed, but it's just moving quickly and stopping, and that is many times required. It's just moving from one point and going to next stage, and sometimes it can go to many Z's. And if that is the requirement, how we can mitigate the problems, the vibration problems, how the machine should be there so that the vibration should not get transferred to the other machines. So that is a big challenge, and one has to understand that. So here we can see is a simple experimentation for characterization, and what we can see is we are just moving a start and a stop. We get this velocity, the acceleration 2g, and of course 5-second delay we introduce and try to move. You can see the settling time is a huge. We didn't use any other kind of damping. Yes, yeah, I think damping is a big problem in this kind of system because the friction is not there. Friction is big dampener. So, but if it's not there, it's required because we want to have better repeatability. But on the other hand, we don't have enough damping. So then we have to introduce damping, either electrical damping or by other means, so that we can get rid of these vibrations, so that it can settle easily. So simple PID control, but these days one can use very advanced controllers and can get that, and a steady error of the order of 1 micron we are able to achieve. Again, we tested for 0.5 G. Here the settling time is reduced, the error is of the same order because it takes time and then it settles. So I think this kind of problems, this kind of projects expose us and let us learn a lot of things about the state of the art, about the systems we want to build. And of course, many of the things which can be simply spin off, and we can have a different products for different applications. One can start gently and develop a system. So maybe one axis, then one can go for 2 axis systems, and then one can embed the third axis. And many of these diamond turning machines, and so even the machine tools, they need that, not only for the production or for the inspections, even the high-end measurement systems, SEM, and even this CMM machines. So it's there, and I think once we are aware of, once we are exposed to the technology, and these things are, I mean, it's not everywhere, it's not taught everywhere in India, but I think this is the time we should start focusing on and start learning about these tools, because this is what makes the modern machines. And these machines are required not only for achieving higher precision or any other thing, or just out of fancy, but it's all to also to support the various initiatives what we have, and also to support the industry which is coming now, the semicon industry, the electronic industry, and even our labs, research labs, they need the support, ISRO there, and like DAE, DRDO. So they need all these advanced tools and advanced systems, and unless we start building it, it's very difficult to support them locally. Of course, things can be bought from abroad, but yes, we have to pay a lot of money and it can be very costly. So to start with, we can always leverage on what we have been discussing in this course, and can work on projects or on products. Uh, so just to give more insight, you can always refer to these two articles, easily available. So this was so whatever I presented today is from or in the previous class is from these two. It's already in the public domain. So a lot of work by Professor Slocum in precision machine design you can find. And if you want to know more about the air bearings, there are a lot of materials by Gross. Of course, unfortunately, it was there available, but many times these books these days not available. But if you search enough, you may be able to find it. So these are the reference material you can always look at. So a lot of material from internet, a lot of companies working, New Wave Bearings, Aerotech, Rockwell Automation, Newport, Dover Instruments there. So many leading companies and a lot of literature there. So one can always look at those literature, those reference materials. So we cover air bearings and guideways, and we also talk about some case studies, some developments, what I worked on previously. And so now we'll move to next topics, and we'll talk about dynamics and different kind of actuators, and we'll take up more examples. Thank you.